We've made it into chapter 9 of Thomas's calculus, and Thomas from beyond the grave is going to lead us through a little bit of a study on differential equations. And we've already looked at some differential equations. We've looked at separable differential equations. In chapter 9, he gives us one other kind to look at, and also some other ways to look at differential equations. Those two ways are the topic of our screencast today. So I'm going to go calligraphy pen because I like it. We should talk about what a differential equation is. A differential equation is just an equation involving a derivative, which seems straightforward, and indeed it is. Any equation that involves a derivative is a differential equation, sort of by definition. Normally the goal for us is to solve the differential equation, and when we look to solve the differential equation, we look to find a function or a family of functions that have the derivative in question. So, two ways to do that. One is geometric. We're going to take a look at that. That is what we call a slope field, and this will be familiar to everyone who took AP Calculus AB. The other is numerical. This is something called Euler's Method, and this is something only familiar to students who have studied AP Calculus BC. So a slope field is a geometric thing. This is a set of coordinate axes. Let's pretend that I would like to see functions whose derivative is negative 2x. I'd like to see functions whose derivative is negative 2x. And we'll just pretend this is 0, 1, 2, like so, maybe 1, 2, maybe I go -1, maybe I go 3, and there are lattice points. These are just points on the grid, and I'd like to sort of envision families of functions whose derivative is negative 2x. Well, one of the ways we can do this is by making a slope field. And the way we make a slope field is at every one of these little dots, we draw a teeny tiny piece of tangent line to what would be a curve. How do we know how to make the slope of that tangent line? Well, this tells us how to make the slope of the tangent line. So for example, everywhere x is 0 at each of these 5 points, the derivative will be negative 2 times 0, and that's 0. And so I can draw little teeny tiny pieces of tangent line like so. When I take a look at all of the places where x is 1, well, negative 2 times 1 is negative 2, so all of these lines will have slope negative 2. Similarly here, all of the slopes are positive 2 over here. Think about what the slopes are here. That's right, those slopes are negative 4, which is much more vertical than negative 2 is. And similarly, the slopes here are positive 4, going straight up like that. You can tell why it's called a slope field. It's called a slope field because it's just a giant field with a bunch of slopes in it. But here's the kicker. I can imagine what solution curves look like just by following the little lines there. Like I know that every time I draw a curve that satisfies this differential equation, it's going to be flat right at the axis. So I can sort of imagine that a solution curve is going to look like so. Or a solution curve is going to look like so. And I can imagine how these curves look. They all look like so. Now, we sort of knew this was coming. How did we know this was coming? Well, we can figure out what y is. y is the antiderivative of that. And so all of the green curves should look like this. They should. And you can see that they do just by following the little dashes. Okay, so just trying again, let's pretend that this is the slope, 1 minus y. And I'll just come up with a whole bunch of dots again. This is 3, 2, 1, 0. And you can do this anywhere on the grid. Nothing special about these points. So just considering, everywhere y is 1, dy dx is 1 minus 1, flat tangents all the way through there. And when y is 2, these slopes have -1 because 1 minus 2 is -1. And these slopes are 1 minus 3. That's -2. What happens here when y is 0? When y is 0, the derivative is 1. And then down here, the derivative is 2. Each time, the slope of the tangent line is 1 minus the y value. So if I ask, what is a solution curve going to look like going through that dot right there? Well, going through that dot right there, it's got to have a slope of 1 coming through there. And we imagine that as we get closer and closer to here, we've got to flatten out, because if we were ever to get to y equals 1, it would flatten out. This is going to be a horizontal asymptote, so it's got to look like this. And then the slopes get more negative as you go down, so we're imagining something that looks like that. Similarly, if I asked for the solution curve that goes through -1, 2, I'd imagine something that comes through like so and flattens out. Horizontal asymptote at y equals 1. Okay, we'll go one more. We'll go one more. Oh, sorry. Let's imagine that dy dx is x minus y. And let's imagine that we're going to do it in a -2 to 2 window. Take a moment, figure out what the slopes would be, and in about 5 seconds, the whole thing is going to be done. So really, hit the pause button. Hit the pause button. I mean it. Hit the pause button. I mean it. Hit the pause button. See, I told you were going to miss it. You were going to miss it, and you did. So there. Okay. So that's that. If I want to imagine a couple of solution curves, if I imagine the solution curve passing through this point, I know it's got a bottom out here. I know the slopes get steeper as we move left. And I know I've got this slant asymptote sitting right here. So I'm imagining a solution curve that goes like so. Similarly, if I'm trying to imagine the solution curve that goes through here, I'm imagining there's a slant asymptote here, so we've got to get closer and closer to the slant asymptote. And as y gets bigger and bigger in a negative direction, this gets worse and worse in its slope. Okay? Okay. So that's the way the geometry works. If we're looking for a numerical method, and we might be, if we're looking for a numerical method, yep, we are. I would like to outline for you something called Euler's Method. Euler's Method named after Leonhard Euler, who did an awful, awful, awful lot. The basic idea is that we use teeny pieces of tangent lines to approximate solutions. And the basic idea here is a Calc 1 idea. Differentiable functions are locally linear. So in very small intervals, there isn't much difference between the function and its tangent line. So consider the following. We're going to let dy dx be x plus y minus 1 with y of 1 equal to 1. I want to use Euler's method with two subintervals. Oh, wow, I don't know what I just did. There we go. With two, that's what I did. With two subintervals, sorry folks at home, to approximate the y value at 1.2. And so here's the basic idea. Here's x equals 1. Here's x equals 1.2, figure not drawn to scale. Clearly, the two subintervals would be from 1 to 1.1 and from 1.1 to 1.2. The function is 1 at 1. So maybe this is the 0.11. Since the function is not much different than its tangent line in a very small area, we're going to draw in that little piece of tangent line. What is the slope of that little piece of tangent line? This tells us what the slope of that piece of tangent line is. The x value plus the y value minus 1. And in this case, that happens to be 1. And so we are going to assume, for argument's sake, that the function in this small interval is a line segment with a slope of 1, because that's the derivative at 1, 1. So the question is, what is the y value at this point? I mean, we're all pretty sure that this is 1.1 comma something, but what's the something? And the answer comes from a little bit of 9th grade algebra. We know that the change in y over the change in x is the slope. And we know what the change in x is because we can measure it. So the change in y must also be 0.1. And if the change in y is 0.1 and we started at 1, then the new y value must be the old y value plus the change in y. Are we okay with that? I'm going to say that one more time so you don't have to rewind it. Since the change in y is 0.1 and we started at this y value, the new y value is the old y value plus the change in y. And then we do the same thing all over again. We do the same thing all over again. We're going to come to this point here and figure out what the slope of the tangent line is. Slope of the tangent line is the x value plus the y value minus 1. 1.1 plus 1.1 minus 1. That's a slope of 1.2. That's a slope of 1.2. And I know from 9th grade that the change in y over the change in x is the slope of the line. And I know what the change in x is because I can see it. And so I know what the change in y is just by cross multiplying. So here's the deal. If we started at this y value and we went up that far, then the new y value, which is approximately the y value at 1.2, is the old y value plus the change in y. and we have an approximation for the y value at 1.2. An approximation. Now, I know what you're saying. You're saying, hey, you couldn't do that again, and you are just wrong. You are so wrong. Of course I could do that again. Let's assume that dy dx is, I don't know, what do you want to make it? Some derivative function. Oh, just throw it out there. X minus y. That's a great idea. X minus y. And we're going to let the y value at 1 be 1, and we're going to let the change in x be 0.5. We're going to find an approximate value for the y value at 2. And so again, oh wow, is that ugly? And so that's not much better. Here's 1, here's 2, here's the 1.5. That's our delta x in action there, 2 subintervals. So here's 1, 1, looking for the slope of the line. Well, the slope of the line is the x value minus the y value, and in this case, that's 0. Not a whole lot of calculus going on here because the slope is 0. So the change in y over the change in x is the slope of the line. We know what the change in x is because we can read. And so there is no change in y. And so this point has coordinates 1.5, 1. There is no change in y. So whatever this y was, this y is. Now we come to here. We want to draw a little tiny piece of tangent line. How do we do that? Well, x value minus y value. That's a half. That slope is a half. So the change in y over the change in x is a half. And I know what the change in x is. And so the change in y is 0.25. So I'm looking for an approximation for y of 2. I know that the old y value is 1. I know that it went up by a quarter. The approximate y value is 1.25. How about that? The upside for you is that this process runs exactly the same every single time. Every single time. Okay? Time for you to consider some stuff. You should consider some stuff. Let's get a slope field for this differential equation where dy dx is x plus 1. And then let's use Euler's method to approximate for this differential equation. Let's approximate the y value at 2 if the y value at 1 is 2 and delta x is 0.5. So let's use 2 subintervals. Okay? So on your own, you're going to generate a slope field for this. Maybe in the -2 to 2 window would be fine. Dy dx is x plus 1, and then use Euler's method to approximate y of 2 if the function goes through 1, 2, and that's your delta x. So 2 subintervals. Okay? Great. I'll see you next time. Thanks, everybody.